this video, we're going to discuss Torricelli's law or Torricelli's theorem. This is a special application of Bernoulli's equation. So Torricelli's law states that the velocity of a fluid passing through a hole in a tank is the same as the speed a mass would acquire when free falling from height h. So what that means in casual language is that we are trying to find the velocity of a fluid as it exits the hole in this tank. And we can do that by thinking of the fluid as a collection of particles or molecules that have mass. And so that would be like the same as if a mass went up in a roller coaster and fell a height h, what velocity would they have at the bottom of the roller coaster? And that's what we're going to talk through, what that velocity would be. So we're going to start by identifying two points, just like we did with Bernoulli's equation. And point 1 is going to be inside the tank at the top of the water level. And the assumption is that the water is still with a velocity of 0 at point 1. Point 2 is going to be at the hole, but like slightly outside the hole. And then we're going to draw horizontal lines so that we can identify an h equals 0. And I'm going to make h equals 0 at the height of the hole. And so now we can apply Bernoulli's equation, and let's talk through that. So at point 1, inside the tank, there is no air, or there is no water pressure, but there is air pressure, 101,325. And I do have height because I made this h equals 0, and we're just going to write it conceptually as rho gh. And there is no velocity because we assume the water is still. And then we get to spot 2. At spot 2, we're right outside the tank, so there is air pressure, 101,325. There is no height because we made it h equals 0, and we would be solving for that velocity. So you can see from the equation that the 101,325, the air pressure is going to cancel because it's on both sides of the equal sign. That leaves rho gh equals 1/2 rho v squared, and the density of the fluid is going to cancel. And the velocity then of the fluid coming out of the hole is going to be equal to the square root of 2gh, where h is the height of the fluid that is above the hole. And we can use this little shortcut to always calculate the velocity of the fluid coming out of the hole. But you do need to be able to derive the equation in order to use it. Let's look at an example. A large tank of water is open to the air. The tank is 5 meters high and the tank is punctured 2 meters from the ground. At what speed does the water emerge from the hole? So let's start there. And since we just talked about it, I'll go a little bit quickly here. So again, I need to pick 2 spots. And the secret spots are going to be inside the tank at the top of the water level and at the hole, but right outside the tank. And then I'm going to draw horizontal lines so that I can choose an h equals 0. Now I'm ready to apply Bernoulli's equation. And at spot 1, I do have air pressure because the tank is open, 101,325. I do have some height because I made this h equals 0 and I'm above that height. And I don't have any velocity because there's an assumption that the water in the tank is still. And then at spot 2, right outside the tank, I have air pressure, 101,325. I don't have any height because I made that h equals 0, and I'm solving for that velocity there. So you can see again that the air pressure is going to cancel, and I end up with rho gh equals 1/2 rho v squared. And just like when you do conservation of energy, how the mass term often cancels, so the density of the fluid is going to cancel here, and I end up with gh equals 1/2 v squared. Now when it's time to plug in my numbers, I have g of 9.8, but this h is defined as the height of the fluid above the hole. So if this is 5 meters and we punctured the tank at 2 meters, that means that h value is 3. And that gives us the velocity of the water coming out of the hole of 7.67 meters per second. So now I know the velocity at which the water is exiting the tank, and I added that to my picture and labeled it as Vx, or the horizontal velocity is 7.67 meters per second. So now part B says, what horizontal distance does the water travel? So I'm actually solving for this horizontal distance that I labeled as dx. This is now classic projectile motion. And if you forgot how to do projectile motion, this is a really good time to review. So in order to find dx, I'm going to need to know the time it takes to parabola down. But I don't know that time, but I do know that it's equal to the time it takes to just fall straight down. So instead, I'm going to calculate the time it takes to fall straight down, which I can get from d equals 1/2 at squared. It is falling a height, or a distance, of 2 meters equals 1/2 times 9.8 t squared, and it takes 0.64 seconds to fall straight down. That means it takes 0.64 seconds to parabola down, and it also takes 0.64 seconds to travel in this horizontal direction. We also need to remember that when something is in projectile motion, that the horizontal velocity is constant. So therefore, I can use the constant velocity equation to solve for dx. So I have velocity as distance over time. I'm solving for d, which is going to be equal to the velocity, 7.67, times the time, 0.64, and I get a horizontal distance of 4.91 meters. So part C says, what is the speed of the water when it hits the ground? So we're looking for the speed down here when it hits the ground, and we know that the horizontal component of the velocity does not change. So that's going to be 7.67 meters per second. But we also know that the y component does change. It goes faster by 9.8 meters per second every second that it's in the air. So we can calculate that velocity in the y direction with our first acceleration equation. So I wrote down VF equals VI plus AT, and since we're just pretending that it's falling straight down, the initial velocity is going to be 0, and it was in the air for 0.64 seconds times 9.8, so this y component is 6.27 meters per second. So now the resultant velocity, or the final velocity when it hits the ground, is going to be the resultant of the x and the y component. And we can find the answer to that using Pythagorean theorem, and we get a c value, or a resultant velocity, of 9.91 meters per second.